I'm going to be solving question 74 from the night textbook. This equation states a block on a frictionless table is connected as shown in the figure, which I've drawn here, to two springs having the spring constant K1 and K2. Show that the block's oscillation frequency is given by F equals the square root of F1 squared plus F2 squared, where F1 and F2 are the frequencies at which it would oscillate if attached to the spring 1 or spring 2 alone. So for this equation, we're going to want to use the simple harmonic motion frequency equation, which is F is equal to 1 over 2 pi times the square root of K over M. Now, since the question asks us to find F1 and F2 if springs were separated, we're going to have two equations. So we're going to have F1, K1, as well as F2 and K2. And we can assume that K is equal to K1 plus K2. So therefore, we can derive the equation F is equal to 1 over 2 pi times the square root of K1 plus K2 over M. So our goal for this question is to prove that this equation can give this equation. And so in order to do so, all we have to do is plug F1 and F2 into this equation, and hopefully in the end we'll get this. So that means F is equal to the square root of F1 squared plus F2 squared. Oh, don't forget your pi. So now we're just gonna simplify this equation and solve. So first we can start with 1 over 2 pi squared plus 1 over 2 pi squared. We're going to want to move that out of from underneath the square root. So we just rationalize it, and we can get 1 over 2 pi. Then we have the square root of K1 over M squared. So anytime you square a square root, it just becomes itself. So K1 over M. Same thing over here, K2 over M. And because these are common denominators, we just combine the two and we get 1 over 2 pi times the square root of K1 plus K2 all over M. Therefore, that means that the block's oscillation frequency equation can prove that this is a frequency if the springs were alone.